All right. In a previous lab, Lab 7, we learned how to collect high-resolution radio spectra using the 20-meter diameter radio telescope at Green Bank Observatory in West Virginia. In these spectra, we were looking for the 21-centimeter emission line of cold neutral hydrogen gas. Now, in that lab, we were looking at hydrogen gas in our Milky Way galaxy. And that gas is relatively nearby, and so it was very easy to detect. In this lab, we're going to try to detect the same hydrogen gas, but from a much more distant, faraway galaxy. This requires taking a slightly different type of observation. Instead of doing a tracking observation, we're going to do what's called an on-off observation, for reasons you'll see. Okay, so first, go to Skynet, and under My Observatory, go to Radio Observing. We're going to add a new observation. Now for the target, you'll want to pick a galaxy in the list that's provided in the lab. I'm going to do a different galaxy. I'm going to do Messier 83. I'm going to search for it. There it is right there. We can see it's entered the coordinates, the right ascension and declination of the target. We have an observation name. And then we want to make sure that these two numbers are 10 and 15 respectively. The first number is the minimum sun separation. So here we're insisting that the sun be at least 10 degrees away when we take our observation. Now, radio astronomy you can do during the day. And there's a good chance your observation will be carried out during the day. But the signal that we're looking for is very faint, and it becomes challenging to detect that if you're too close to the sun. The sun is incredibly bright at radio waves, and sometimes those radio waves can bounce off of the support structure that's holding up the receiver and get into the receiver, messing up your observation. So you want to make sure you're 10 degrees away from the sun or more so that doesn't happen. Now, if your target is currently within 10 degrees of the sun, it's just not observable this time of year. It will take some time before the sun moves away from it in the sky, in which case you'll want to pick a different target. And you can check that. Come up here to the map and advance in time until you find your target. And the sun is the yellow dot here. I'll zoom in. And we are more than 10 degrees apart. Each of these boxes is 10 degrees across and 10 degrees up, down. So this target is indeed observable this time of year. Now your min target elevation, you want to make sure your target is more than 15 degrees above the horizon. If it's too low in the sky, the telescope will start to pick up the surrounding mountains and the ground. If I come down here to the air mass chart, we see that this target gets above 15 degrees for about 4, maybe 4.5 hours every day. So it's indeed observable. Okay, save and continue. Now we're going to set the spectral settings. You want to set this to high resolution mode. Our receiver data acquisition mode should be high resolution. And you may remember it takes 2 high resolution spectra back to back in frequency. The first one should be centered on 1406.25 and the second one on 1421.88. Your hydrogen line will most likely be in the second one unless you're looking at a very high redshift galaxy, in which case it'll be redshifted down into the first spectrum. Channels can be 1024. We'll save and continue. If you have multiple time accounts, pick one. And then we select our path type. Previously, we did the tracking mode. We just observe for a certain amount of time. But here we're going to use the on-off mode. This is because the signature that we're trying to detect is so faint, it's difficult to see in a regular spectrum for reasons I'll show you in a second. So what we do is we do a certain amount of time on target, then we move the telescope over and do a certain amount of time off target. We can then combine these two spectra to make it easier to see the emission line from the distant galaxy. So in this case, we're going to do a 60-second observation on target. We're going to move the telescope 2 degrees in right ascension, 0 degrees in declination. So it moves the telescope off target, and it will collect another 60-second observation off target. Then, as I said, we will combine these in such a way to cancel out all the things we don't want to see, making it easier to see the thing we do want to see. Repeat can be set to 0. Integration time can be 0.3. Save and continue. And submit the observation. So there it is, ready to go. Here's one that I just took. So when you come here, you click on this link. Now, if you get a broken link, that means something went wrong, and you should go back and resubmit the observation. But hopefully you end up on this page. Now, if we come down here, before we look at this, we can look at the on spectrum and the off spectrum separately. Here's the on spectrum. This is the hydrogen line, not of our distant galaxy, but of the Milky Way. We have to look through the Milky Way to see the distant galaxy. So we will pick up a lot of hydrogen in our own galaxy, and that's what we see here. The hydrogen from the distant galaxy is actually this little bump right here. Very hard to see. You wouldn't know that that is that unless I had told you. It's lost in the variations in the spectrum. These background variations are not astronomical or astrophysical, but instrumental. They're caused by the instrument itself. Here in the other spectrum, you can see the variations. It's simply an effect of the instrument. So then we move over and we collect the off spectrum. It looks almost identical, except the little emission from the distant galaxy is not there. And then on this page, they're combined. We take the on spectrum, subtract the off spectrum, canceling out most of that variation. We then take that difference and divide by the off spectrum. That flattens it out, and we get this. The hydrogen line from the Milky Way almost perfectly canceled, not quite, but almost perfectly. And the background variations almost perfectly canceled. Not completely, we still see some variation here and down here, but it's a lot better than it was before. And because of all this, we can now see the hydrogen line of the distant galaxy. And one thing you may notice, it's a lot broader than the hydrogen line of our Milky Way. This is because the entire galaxy fits within the beam of our radio telescope. So we're seeing both the side that's moving towards us, rotating towards us, it's blue shifted, and the side that's rotating away from us, and it's red shifted. So this broadens the line. This side of the line corresponds to the side of the galaxy moving towards us, and this side corresponds to the side that's moving away. In some cases, this effect can be really extreme, and you get a horn-shaped profile where you have more emission on the wings than at the center. You see it a little bit here, a little dip there in the center. And of course, you notice that it's not at the same place as the Milky Way's emission line. That's because this distant galaxy is redshifted due to the expansion of the universe. Okay, that's it for this video.